Hello everyone, welcome to the third lecture in this series of lectures where I am talking about the deformation theory of instantons on nearly G2 manifolds. So in the first two lectures we covered the introduction, so we just saw an introduction to G2 structures and we focused on the ones that we are interested about, that are the nearly G2 structures. Then we also saw two equivalent definitions of G2 structures and in particular nearly G2 structures. We also, in the second lecture, we saw the definition of an instanton on a manifold with a G2 structure, and then we also talked about the infinitesimal deformations of instantons on nearly G2 manifolds. So we saw how we could relate the deformation space to the kernel or the eigenspace of a Dirac operator or a family of Dirac operator. So we saw that if epsilon is an infinitesimal deformation, then they should satisfy this eigenspace condition. So this is how we said that the deformation space was equal to the eigenspace of a Dirac operator. All these Dirac operators were related. So if it's an eigenspace for one t, then it is an eigenspace for all the t's. So we saw all of this, and then today we will be focusing on applying this theory that we have developed to a known example of instanton on nearly G2 manifolds. So we'll be focusing on homogeneous nearly G2 manifolds, and on homogeneous nearly G2 manifolds we have a characteristic connection, which is the characteristic homogeneous connection, and that connection is the same as the canonical connection that we discussed in the previous lectures for nearly G2 manifolds, and thus it's an instanton. And we can talk about the deformations of that particular instanton. So for that, first of all, we will see what are the homogeneous nearly G2 manifolds, and in fact we have a classification. So Friedrich, Karp, Moriano and Simmelman, they classified all the compact and simply connected homogeneous nearly G2 manifolds. So in particular there are 6 of them. So the first one is just a round sphere, which is just spin 7 mod G2. Then we have the squashed sphere, which is sp2 cross sp1 mod sp1 cross sp1. Then we have the Berger space, SO5 mod SO3. We have the LFO log, the SU3 cross SU2 mod SU2 cross U1. And so on LFO log, for k and L both equal to 1, there are two different nearly G2 structures. This one is the 3-Sasakian one. Don't worry about it if you do not know it, but you can just know that for N11 there are two different nearly G2 structures. One is given by this homogeneous structure and the other is given just by SU3 mod U1 KL, where U1 is embedded inside SU3 via this embedding. And the last one is just given by SU2 cube mod U1 square. So these are the 6 homogeneous nearly G2 manifolds, and on these homogeneous nearly G2 manifolds, they are all reductive. So by reductive I mean that if they are written as G mod H, then I represent by the frac symbols the Lie algebra of the Lie group. So frac G is the Lie algebra associated to the Lie group G, and frac H is the Lie algebra associated to H, and this is space M. This is orthogonal to H via the Killing form of G. So since all of these Lie algebras are semi-simple, they have a Killing form, and the Killing form is negative definite, and thus we can treat the Killing form as a metric on the Lie algebra of G, and it gives an induced metric on G mod H, and we see that M is the orthogonal of H, and this is the 7th dimension, and this is basically is the tangent space at identity or EH for G mod H. So this is how we can define this orthogonal space M. And now, as I already told you, that the characteristic homogeneous connection on these reductive homogeneous spaces for nearly G2 is the same as the canonical connection, and since we have that the uniqueness properties of the canonical connection, it's not very difficult to see. We can see that the characteristic homogeneous connection, it always is totally skew symmetric torsion, and in this case it also has holonomy inside G2. So that's why it has to be the canonical connection, and it's an instanton. So what we will do now is that we will consider this characteristic homogeneous connection or the canonical connection, they are one and the same things, on these homogeneous examples, and we will consider them as connections on two different bundles. So the first one bundle that we'll be considering will be just the usual, the G cross at M with the structure group H. So this is sort of just a tangent bundle. And the other one, we will use the fact that this group H that we have, it's a subgroup of the Lie group G2. And thus we have an isotropy homomorphism from H to G2, and using this isotropy homomorphism we can also create another associated vector bundle given by this, and on this vector bundle the structure group is G2. So we can see this we can see the same connection with two different structure groups on two different bundles. And now so now we have two problems. We have two different bundles, we have the connection, and we know that it's an instanton on both of them. We can now try to find out the deformation space by using the formulation that we have created in the past lectures. So this is the main aim for this lecture. So let's begin. And yeah, but there is one thing that we need to discuss first. So I told you there are 6 homogeneous spaces, but there is a problem. Only 4 of them are normal, and by normal I mean that the metric is induced by the Killing form. The nearly G2 metric is induced by the Killing form. So I told you in the previous slide that since all the Lie algebras here are semi-simple, the Killing form induces a metric on the manifold, but it might not be the nearly G2 metric, it can be any metric. So for the first 4 homogeneous spaces, the nearly G2 metric is induced by the Killing form of G. So for these 4, and that is what I mean by normal. So this is what is called normal, and it's induced by this. But for the remaining 2, this is not the case. The remaining 2 are not, the Killing form does not induce a nearly G2 metric. In fact, it's a different metric. So that's why the methods that we'll be using, so we'll be using some representation theoretic methods. We will try to represent the deformation space, the kernel or the eigenspace of the Dirac operators in terms of Casimir's and using representation theory, but that can only be done when the metric is normal. So that's why our methods work only for the first 4 spaces. For the other 2, the L of Warlock and the SU2 mod U1 square, our methods don't work, so we cannot use the method that we developed. So let's move on. So this is the theorem that we aim to prove. So we have computed the deformation space for all of these 4 normal homogeneous spaces. So for the round sphere, we see that now. So here you see that there are 3 columns. The first column is just the homogeneous manifold. The second column is the deformation space in the case with the structure group H. So as I told you, we'll be dealing with 2 separate questions. We have 2 different bundles, and we will like to see the deformation space of the canonical connection in both these situations. So the first one is with the structure group H, and the second one is with the structure group G2. So for the round sphere, there are no deformations. When I say 0, that just means it's a trivial, basically no deformations. And for the Bourget space, there are no deformations for the structure group H, but there are deformations in the structure group G2. One more thing that is good to observe here is that since H is a subgroup of G2, the deformation spaces the deformation space in the second column, for example, will be a subspace of whatever we have in the third column. So because of course since H is inside G2, if there are deformations in that direction, then they will also reflect in the G2 case. Okay, so now similarly for the squashed sphere sp2 cross sp1, 1 sp1 cross sp1, we have for the H structure group, we have this the real part of the 5-dimensional irreducible representation of sp2, which we can represent in terms of highest weights by v0, 1, and In the G2 case, we have the joint sp2 plus a joint sp1 plus again the same. So of course that has to be there. And for the last one, the LFO lock, again there are no deformations for the H case, but there are deformations in the G2 case, and which are just written here. Okay, so these are the deformations. This table does not make much sense now, but I promise that at the end this table will make a lot more sense. And one thing, and then there's one more thing, that so if you remember, we say that there are only 4 normal homogeneous spaces, and we left that for the 2 of them our methods don't work. But luckily we had proved a theorem in lecture 2 that if the structure group is abelian, then the instanton must be rigid. So for the 2 non-normal cases, if you look here, H is abelian in both these cases. So since H is abelian in both these cases, we can actually answer the question for the first bundle, because here the structure group is H, which is abelian. So we know that the connection has to be rigid, so there are no deformations. But we do not know anything about the G2 case. So for the G2 case, we cannot say anything. So there might be deformations, there might not be deformations. We don't know. Okay, so now let's see how we can prove such a theorem. If you just observe here that everything written, the deformation spaces written in these 2 columns, they are represented as the representations of the Lie group G. So everything here is for G mod H, they are the representations of the Lie group G. And how and why we can do this, I will discuss it here. So just to recall, this was the condition for epsilon to be an infinitesimal deformations. We saw that epsilon must follow this. Eta is just the killing spinner associated to the nearly G2 matrix, and then we saw that this is the identification that we have. Now on this homogeneous space, we can denote the tangent bundle via this associated vector bundle, and on this associated vector bundle, we can have a left regular representation rho L of the Lie algebra H or the Lie algebra G2. So on this tangent bundle, the Lie algebra of H and the Lie algebra of G2, they both act via the left action, and when we write E, we denote by this capital E either H or G2, since we are dealing with 2 of the cases and it's not always necessary to differentiate between both of them. So when there is no need for differentiation, we will just write E. When there is need for differentiation, we will write Lie algebra of H or Lie algebra of G2, and thus we can have these associated vector bundle, which is given by this. And on this associated vector bundle, since we are dealing with the canonical connection, we can make use of the properties of the canonical connection or the characteristic homogeneous connection to describe this rough Laplacian in terms of the Casimir operator. So we have these semi-simple Lie algebras, the Lie algebra of G and the Lie algebra of H, and we have the Casimir operator, and then we can actually just use the formula of the rough Laplacian and the fact that we are on the canonical connection to write the rough Laplacian in terms of this. So this is what not just so actually we take these 2 terms, we take the rough Laplacian, and since F is also the curvature of the characteristic homogeneous connection, which is also well known, we can just use, so for the 2 terms that I have underlined in the first line, we get if we just merge them, write everything in terms of the Casimir, merge them, at the end we get this. And here this we know that it will be an eigenvalue for the Dirac operator because of this identification that we have on the top. So for t equals to -1/3, we know it will be if epsilon is an infinitesimal deformation, then it will be an eigenvalue. So this will be some scalar multiple of epsilon dot eta when we subtract it from 97/9, which we have on the right hand side, and this comes from the Schrödinger-Lishnover type formula that we discussed in lecture 2. Then we get this equation, and in fact what we get is that this term is exactly 49/9 epsilon dot eta. So if you work it out, which is not very difficult, then you get that this term is exactly 49/9 epsilon dot eta, and that means that for epsilon to be an infinitesimal deformation, the Casimir thing, the rho L Casimir G must be equal to rho E Casimir H. So here this Casimir H, this is again the Casimir of the Lie algebra of G, but we have just reduced it to the H basis. So since we can distribute G as H plus M, so we have just used the we have just used the H basis of the sub basis for the Lie algebra of G. So this is the condition. Now we have reduced the instanton condition, or being an infinitesimal deformation, to this Casimir condition, but again this is only necessary, it's not sufficient. So if epsilon is an infinitesimal deformation, then we know that it must satisfy this Casimir condition. But if epsilon satisfies this Casimir condition, then we don't know whether it's an infinitesimal deformation or not. The reason being, we are dealing with the square of the Dirac operator here and not the Dirac operator. So that's why it's not a necessary condition. It's not a sufficient condition. It's just necessary. Okay, but nevertheless, at least it will give us a hold on what the deformation spaces will look like. And now, another thing. So now here, if you look at this Casimir condition, we already know what is rho E. So we know what is rho E because that is just the joint representation of the Lie algebra of H or the Lie algebra of G2. So we already know what is rho E. What is unknown is this. So this is the unknown. We do not know what are the left regular representations of the Lie algebra of G or the Lie group G, which will satisfy this condition. So that is what we need to find out. And why do we need, why is that same as finding the infinitesimal deformations? Because the infinitesimal deformation epsilon is an at p valued one form. So it's an M star tensor at p, which in this case is just M star tensor H. So if it's an basically M star tensor E, not just H, but M star tensor E. So it's a section of this, and the sections of this we can write it as a left regular representation. That's just the induced representation, if that's the more familiar one. And now we just want to know that what are the induced representations which will be a part of this section, the space of sections that will satisfy this this condition. So that's why the result that we got, the spaces that we get, are representations of the Lie group G. So the actual calculations, they do not matter much. Rather than what matters is the philosophy behind the usage of the representation theoretic arguments. Okay, so so now we need to solve this equation. We need to find this this left regular representation rho L that will satisfy this Casimir condition for, and we will have two separate situations, one for E is equal to the Lie algebra of H, and another one will be for the Lie algebra of G2. So this is what we do, and once we find all these left regular representations, we know this space. So because from here it's very evident to see that whatever L satisfy this Casimir equation, for if epsilon is in that L, then it will satisfy this then it will be an 49/9 eigenspace of this kernel of this Dirac square. So now these are all the L's that satisfy the Casimir equation, right? And since it's a square of the Dirac operator, we can obviously break them in two parts. And since these Dirac operators are also associated to each other, since they all come from the same family of connections, we can write in them in terms of the d minus 1. And why we prefer to use d minus 1? Because eta is parallel with respect to t equals to minus 1. So that just simplifies the computations a bit. So now here we have these two different eigen spaces for the Dirac operator, and the eigenspace that we are interested in, or the ones that constitute the deformation space for the canonical connection, is the first one in the summand, because this is the one that satisfies this eigenvalue condition. So this is so we are interested in the first summand, but we have only computed this. So now we need to figure out that which of the epsilons which are in the square in this lambda square eigenspace of the Dirac square are in the deformation space. And for that, what we do is, first of all, we have this decomposition of this of the space of sections in the kernel of Dirac square, and here this mi, this is the multiplicity of the representation wi. So wi is an irrep of the Lie algebra of the Lie group G, or the Lie algebra of G. It will change, it's the same thing. So we have these, and mi is just the multiplicity. So the multiplicity is given by this formula. It's just the space, the dimension of the it's just the dimensions, or I think it should be the dimension, yeah. So the dimension of the homospace of wi and m star tensor E. So this is how is given the multiplicity. And now what we do is that we know each of these wi's, because we know the lambda square eigenspace of the kernel from our previous proposition. So we know each of these wi's. What we can do is just we can apply the Dirac operator, the d minus 1a, on each of these spaces, and then we can compute whether it lies in the -2 eigenspace or it lies in the +8/3 eigenspace. So from here, so this is what we do. We just compute the d minus 1 can to see whether it is in -2 or 8/3. So it's easier said than done, but it can be done, because since we are working with the canonical connection, which is a very well-known studied connection, we have a hold of it. We know explicitly how we can apply it, and I'll now just briefly describe how we can do that. So for doing that, first of all, so we'll be working with somewhat this kind of a space. So this is miwi, and this is inside these sections of, again, I missed a dimension, but that's here, it's fine. Okay, so, and again we have this this is a space of sections, which is where our epsilon lies in. So now we have this G. If we have a G representation w comma tau, then we can write any section in terms of C alpha phi alpha, where C alpha phi alpha comma w. We can write any section in terms of this phi comma w, where phi is just the homomorphism from w to m star tensor E, H equivariant homomorphism, and w is in this wi. So because this is how we can identify the space of sections. So once we have identified any section, so this is basically our epsilon. We can write our epsilon in this term, in this form, and when we write this, we can apply the canonical connection. So how the canonical connection just acts simply by minus phi tau star xw. So tau star xw will be in w, since tau is a G representation, and tau star is the Lie algebra representation, and then this thing again is in m star tensor E. And once we have this, now we can apply the Dirac operator. So the Dirac operator is given by ei dot nabla minus 1 can phi alpha dot eh, and we already know how to compute the canonical how the canonical connection acts on this kind of section, and then we can just take the dot. So once we have we have done this, we know how to do all of this, because the dot will only act on the m star part. So once we all of this we know how to do, so we can compute the Dirac operator. It's possible to do these calculations, and we can compute the action of the Dirac operator on each of these sections. And now here we only took one element of the section, but it's not necessary that any element looks like this. You might need to extend it by linearity, but it's enough. You can only check it on one of the element, and since these are G irreps, if it will be in either -2 eigenspace or +8/3 eigenspace. So you do not need to check for any general element. You can just pick one of the element and just see the action of the Dirac operator on that. So once we have this, you can also extend it by linearity, and that will tell you whether it's in the -2 eigenspace or +8 over by 3 eigenspace. So this is a very troublesome step, which actually was not required for the nearly Kähler 6 case. So in the nearly Kähler 6 case, Charbonneau, my advisor, one of my PhD advisors, and Derek Harlan, they actually studied the deformation of instantons on nearly Kähler 6 manifolds in 2016, and they applied similar methods. But the good news for them was that in 6-dimension nearly Kähler manifolds, we actually have 2 killing spinors associated to a nearly Kähler 6 manifold, and this implies that the lambda eigenspace of dTA is isomorphic to the minus lambda eigenspace of dTA. So that's why if you can just write this the lambda square eigenspace of d square as 2 times the lambda eigenspace. So from here, what is good is that if you know the lambda square eigenspace, then you already know the lambda eigenspace is just half of it in some sense. So the step 2 of actually computing the action of the Dirac operator on the lambda square eigenspace is not required, which actually saves a lot of trouble, but it's nevertheless can be done. Okay, so this was for nearly Kähler. For nearly G2, however, we do not know of any such relation, and it's very evident from this table. So this table represents the eigenspace for the lambda square eigenspace for the Dirac square and the lambda eigenspace for the Dirac, and from here you can say that there is no relation between the two of them. For some of them it's a proper subspace, for some of them it's exactly the same thing. So there's no such relation, and that's why step 2 is definitely required. Okay, so this was this is how you do these computations. This is how you compute the deformation space for the canonical connection. And now I'll just try to make some sense about the deformation spaces, the spaces that we have got. And the first thing comes from the symmetry action of the Lie algebra of G. So this was proved by Benoit and Derek in their paper, and the same proof applies to the nearly G2 situation. And they say that if we have any element C, which is a lambda 214 add p-valued form, so just lambda 214, as we already saw that this is one of the pieces in the decomposition of the two forms, and if C also satisfies this parallel condition, then this DAIXC is an infinitesimal deformation of the canonical connection for all automorphic vector fields. So if X is an automorphic vector field, then IXC will be a infinitesimal deformation. And for homogeneous spaces, the space of automorphic fields is isomorphic to the Lie algebra of G. So what this proposition says is that for each such independent C that satisfies these two conditions, we will get a G worth of infinitesimal deformations, or we will get this space isomorphic to this Lie algebra of G of infinitesimal deformations. So the multiplicity of the Lie algebra of G in the deformation space is actually equal to the number of linearly independent C's, which satisfies these two conditions. And in fact, if you observe, if one of the candidate for this C is the curvature, because curvature of the canonical connection. So of course, curvature lies in lambda 214 because it's a curvature of an instanton, so it must lie in lambda 214. And the other property is due to the fact that it's a curvature of the canonical connection. So for the canonical connection, the curvature satisfies both these conditions, and that's why it should produce a space Lie algebra of G space in the deformation space. But in fact, this is but in fact they all arise from gauge transformations. So since FA is itself gauge invariant, the deformations it produces, they are all invariant under gauge transformations. So modulo gauge, we get rid of this FA. So this FA does not generate any gauge invariant gauge orthogonal deformations, and that's why we can comment that the multiplicity of G modulo gauge. So if you remember, we had a gauge fixing condition, dA star epsilon equals to 0, and modulo that condition with the multiplicity of G in the deformation space is given by the trivial E reps in this Lie group G2, because these are the number of linearly independent C's, G2 tends to E, sorry, and why it's G2, because this is the lambda 2 14 part and this is the at P part, and this -1, it represents to subtracting the curvature, because that is not gauge invariant. So this is how we can compute the multiplicity of G in the deformation space. And if we look at the table once again, the table of deformation spaces, you see that this is satisfied in all of them. So here we just have this Lie algebra of G, so that comes from the symmetry group. Here again we just have one copy of the Lie algebra of G, and in this we have two copies of the Lie algebra of G. So for the Bourget space, this is how we get all the deformations. For the squash sphere, there's again one 5-dimensional space left, and for the L of Warlock, there's a 2 SU3 left, which we have not accounted for, but we can account the 5-dimensional space that we have in the squash sphere case. That just comes from the lift of the deformation space on the standard AST instanton on the 4 sphere. But for the SU3 case, we still don't know how we get these, from where these deformations arise. This is something that I'm still working on. So this is all I wanted to say, and the one thing that one can observe is that almost all these deformations are genuine. So because we exactly know that what these integrate to, or which is the action that they come from. So except from this one, we know that all of them are genuine, because the deformation space of this is also genuine. And you can just lift the family of instantons from S4 to this squash sphere, and you will get these deformations. Alright, so this is all, and before just leaving, I will just tell some future directions. So for nearly G2, we know that there is an existence of a killing spinner, but for nearly G2 manifolds, you can have up to 3 killing spinners. So each killing spinner corresponds to a different nearly G2 structures, and when you have two killing spinners, linearly independent killing spinners, you have the Sasaki-Einstein 7 manifold. For 3, you have the 3 Sasakian nearly G2, and you can do similar computation or similar you can study similar deformation theory for both of those cases. The other future direction is, of course, just trying to figure out from where this 2SU3 comes from. So this is all I wanted to say, and thanks a lot for listening. This is the end of my lecture series, and please let me know if you have any questions, comments about this, and I'll be happy to answer you. You can email me if you want at ragini.singhal@kcl.ac.uk. All right, thank you so much once again, and have a nice day. Bye.